Boop. Okay, so one of the problems with taking a look at or writing a system as a matrix equation is you can't tell what the dependent variables are, right? And so you can make them up. You can call them X and Y or Y and V. You can call them A and B. It doesn't really matter. But if you start off, like in that case, if you start off with a second order differential equation that you turn into a system of first order, you are defining already what those dependent variables are, and you have to stick with it. You can't change them. You can't swap them around vertically in those column vectors. So you're limited to whatever it is that you started with to begin with. So,
all right. I see now. I just totally missed that.
No, it's a good question. Very good question. Any others on problem set or notes for that matter? Stuff. Did you guys get a chance to at least see that I posted an additional bonus problem that I solved for 3.4 with the imaginary eigenvalues? The problem with that section is it can be overwhelmingly long if you go through and do it the long way where you use both eigenvalues and both eigenvectors to come up with a general solution. That takes forever. And of course, as soon as you do it once, you realize we didn't need to do that anyways. So I made those bonus videos. So if you want to see it, you want to see how it works, you can totally see how it works. And you don't have to write it down if you don't want to. I just wanted to show you kind of how the process works. And that even though it kind of feels like cheating because we're only using one eigenvalue and one eigenvector, it's the complex nature of the eigenvalue and the complex nature of the eigenvectors. That's what makes it so that you wind up with multiple terms. And so you can use that linearity principle to your advantage. So anything else back to 3.1 and 3.2? This is kind of going back to where we were before. A lot of this stuff is just getting comfortable with matrix form of equations, matrix forms of solutions, being able to switch back and forth between the matrix form of a solution and the scalar form or the parametric form of a solution.
I did notice this isn't 3.1 and 3.2, but on the playlist, the videos for parts 3.5 and 3.6, the first two parts are flipped.
Oh, are they?
Those sections.
The order is wrong? Ooh,
yeah.
Thank you for letting me know.
It was a bit confusing in 3.6. I accidentally
like,
filled out part 1 and part 2. Yeah.
You're like, wait a minute, hold on.
It was a whole mess.
You get into a video and it's like, we just left off doing, no, we didn't. We didn't do that. Let me scroll down and see. You said it's 3.5? Or no, not section 3.5. Which one? Section 3?
It's parts 1 and 2 for 3.5 and 3.6.
Parts 1
well, no,
and 2.
3.6 only, I guess. I don't know where.
3.6 as in?
3.6 part 2 is before 3.6 part 1 in the playlist. Like when you're watching
it. Got it. Sorry. Yep. I thought you were saying that the videos were labeled wrong, but I got you.
No,
they're labeled right. They're just in the wrong order.
Yeah.
I changed it, so it should be good now. I just need to hit save and then tell it to do that. Boop. Yay. Thank you very much. Any other questions related to the problem set? We're feeling good about it? Yeah. So. The one problem in there that I think is because it's kind of squishy and sort of ill-defined is number 2, where it's the parameters A, B, C, and D are kind of up to you to decide what they are. But really, it's just a pattern-seeking exercise. I just wanted you to see what happens if A and D are both 0 and B and C are literally opposite values of each other. And you can just see what happens to the DE plot, see what happens to the phase plane. The good news is that as long as the values for A, B, C, and D are as specified, you're going to get a phase plane that has exactly those same characteristics. You could have done that one with the explore command in Maple, and maybe some of you did, I don't know. The downside with using explore in Maple is sometimes the slider bars can get a little glitchy and it's a little clunky. It's not the best in terms of being able to use it for DE plot, but it does work. What's the other one? The other one that tripped people up. No, no, not that one. I guess the other thing that I would strongly urge you to practice as a good method when you're facing a problem that says, do this by hand, don't start off doing it by hand. Come up with what Maple says the right answer is. Do that first. It's okay. You know going into it what you should be shooting for as a solution. And you can even kind of micromanage this stuff bit by bit. You know what your coefficient matrix is, for example, so you can type that into matrix or type that into Maple modified with the, 2 minus lambda and the minus lambdas along the diagonal. Type that into Maple and say, find the determinant for this modified coefficient matrix. It'll do all the work for you. You can totally do that in Maple, especially if you're typing your work in Maple anyways. So use Maple to your advantage, but don't be afraid to right out of the gate say, hey, here's the coefficient matrix. What are my eigenvalues and eigenvectors going to be so that I can show that using the by hand method? I know what I'm aiming for. Too many times people will start off doing it by hand and because I'm going to do this on my own with algebra, and you forget that you can make a mistake and you might not notice the mistake until you're nose deep in a problem. If I had $1 for every time I've had somebody ask me, hey, I'm having trouble trying to get my eigenvectors to work, they're not working, and then you find out, oh, there's a good reason for that. It's because that polynomial you factored way at the top, you factored wrong, right? Your pre-algebra teacher was like, oh God, I can't believe this, right? I can't factor a polynomial with a 1 for leading coefficient, a quadratic with a 1 for leading coefficient, and whole numbers for the other 2 terms. It's okay. If I had $1 for every time that was me, I would have quite a few dollars, quite a few. I won't admit to how many while we're being recorded, but it's a lot. Okay. You couldn't see my eyes, so it doesn't count that way. So, okay. So other than kind of reminding us that, we occasionally suck at algebra, doing this stuff by hand has another purpose. And that is there are some questions that you can't solve by just saying, hey, Maple, will you find the eigenvalues and the eigenvectors for this? Sometimes, like the smudge problem that you guys all responded to in your teams, sometimes the smudge, type of problems like the smudge problem, you have to know kind of how this thing works, how you develop and how you come up with these eigenvalues in order to solve a problem. Because sometimes the problem is midway along the process, putting things together. So one of the things that we'll be working on today are some classwork problems that sort of get at the machinery behind what we're doing and allow us to do more than just kind of grind the wheel. Monkey turns the wheel and the wheel goes around, right? We can do that really, really well because we're good math students. Being able to do the by hand work is really in the service for us, not of learning and refining a particular skill, but of understanding the concept that's underneath it. Right? We want to be able to know how did these eigenvalues come to pass, and then what do they mean? What do the eigenvectors mean? And by the way, eigenvalues and eigenvectors, this is not the only time they get used. They get used all over the place in mathematics, in science. Pretty much all of modern physics requires the use of matrix algebra. All of and by modern physics, I mean anything past about 1790, 1820, somewhere in that range. Anytime you go past that, once you stop talking about Isaac Newton and planets and satellites and you start asking more important questions, bigger questions, harder to decide questions, that requires a whole lot more mathematics. And same thing goes with engineering and all the applications. Finance as well. Finance uses all this stuff all the time. So we're just learning a tiny little slice of where eigenvalues and eigenvectors show up in the world. And I've actually got a video that I'm going to share with you guys that wasn't me. Somebody made this and did a really nice job of kind of laying out all the different ways that eigenvalues and eigenvectors pop up. And most of it you'll be like, I don't understand that. But you'll understand the context. You won't understand necessarily the mathematical use of it, but you'll understand the context. You'll be like, cool, so it shows up over there. So if you take a topology class, it'll show up in there. If you take a fluid dynamics class, it shows up in there. If you take an electrostatics class, it shows up in there. It's all over the place. You can't avoid it. So I would imagine for most of you, this is your first run-in with eigenvalues and eigenvectors. So if you're sitting there thinking, man, I'm barely hanging on. I can kind of wrap my head around this. That's okay. It's like learning long division. The first time you learn long division, you're like, I don't know why we're doing this. I'm just doing what the teacher told me to do. And you do it a couple of times, and then it starts being more familiar. And then pretty soon you're like, this isn't so bad. And then you learn how to do it with imaginary eigenvalues, and you're like, okay, it's not that scary. And before you know, you'll be comfortable finding eigenvalues and eigenvectors by hand or using Maple to make sense of them. And it won't be that scary. And that's kind of the way mathematics and science works, right? You learn the language and you keep using the language over and over until you're not scared of it anymore. And then you can say big things and important things in new ways. So unless anybody has any questions about 3.1 and 3.2, especially the problem set or notes or anything like that, what I want to do is give you guys a chance to, surprise, pop quiz. You didn't see that coming, did you? Or did you read the agenda? Did you honestly read the agenda? Did you see surprise pop quiz? Or did you get surprised? Matthew, did you get surprised? I'm so pleased. Okay, I don't get to use the polling feature in this with you, but I have a very serious pop quiz coming for you, and I cannot emphasize enough how pop this pop quiz is. So here we go. Get ready. Here we go. No questions. Here we go. The poll's up. Question number 1. This pop's name originally was Bib Label Lithiated Lemon Lime Soda and was marketed as a mood stabilizing medicine. I gave you some choices there. Not all of them are directly pop related, as you can see if you scroll down. Some of them are actually mathematical in nature. But I gave you a couple of gimmies. And of course, you guys all studied your pops, so this is no big deal for you. I'll let you, do that. And yes, by the way, you're welcome to use your notes, but no Googling. And we're going to end the quiz in about 7 minutes. So, don't take too long. Austin, did somebody fart? Oh, okay. Because it kind of looks like it. I can't believe you made me do that on video and recorded it. So somebody watching this later is going to be like, dude, totally he farted. Look at what he's doing. He must have farted.
Sorry, we had a sudden influx of a very skunky smell. I don't know where it's coming from.
Did you not just hear that from my stomach?
Oh, I think Matt smells it now. So be sure to submit your answers. You got about 4 minutes, no longer. Got about 2 minutes. If you haven't submitted your answers yet, get on it. Anybody still working? It's hard to tell from my end, so okay. About 2 minutes. So my wife decided to play the Hamilton musical in the background on Saturday, I think. And you know, I'm I didn't think it was all that great, but okay, it's not for me. I get it, whatever. But there are several songs in there that just got like lodged in my head. I can't get them out of my head now. They're like rolling through my head constantly. It's so annoying. This happens to me occasionally. It's the King George song. Da 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 da. Disney, don't sue me if you see that recording on YouTube later. It's stuck in my head.
And I just got that out of my head.
Oh, I'm sorry.
Like,
I'm sorry.
3 hours ago, I got it out after 2 days or 3 days.
Yeah. Usually I'm the guy who like, my wife will be like, I have an earworm that I can't get rid of. And I'll be like, oh, what is it? She knows better now. She doesn't tell me, but because I'll wait like an hour later and I'll be like, da, 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 da. She's like, stop it. Okay, so how we doing? We got like 30 seconds. Anybody still working? We're all done. Everybody done? Everybody answered. Okay, Emma, you joined us. Do you see the pop quiz? Come on, Emma. She's having connectivity issues. I shouldn't pick on her, I know, but you know, when it's just the screen, what are you going to say? Well, Emma, if you can't see the pop quiz, we'll read through the questions here in a second. We're actually going to take a look at the poll and take a look at the results. So ended the poll. So let's take a look at the results, share the results. Boop, 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 boop. Oh, hey, and Dr. Butler's joining us. Hey, how's it going, Dr. Butler? I invited Dr. Butler, my dean, to come and enjoy a little bit of differential equations. And so you're joining us just as we're about to review the results of a little pop quiz. The first question, this pop's name was originally bib label lithiated lemon lime soda, and it was marketed as a mood stabilizing medicine. Of course, the correct answer was Sprite.
Who said Dr. Pepper for a
No,
lemon lime?
the answer
soda?
wasn't Sprite. The answer is 7-Up. That's actually the answer, 7-Up. Have you ever had a 7-Up before? I mean, do they still make it, right? I'm pretty sure it's still in the stores. But 7-Up was like, it started off as this like medicinal thing. And so it had this crazy name. And then somebody was like, no, you need to name it something else. And so I don't know where they came up with the 7-Up from. Maybe they looked at like a elementary school classroom when they heads up 7-Up, you know. Anyways, okay, so that's the first question. So that was a pop related question. Second question, if we only know that 2 plus 3i is an eigenvalue for the coefficient matrix, that's all we know. We don't know anything about the coefficient matrix. What else can we say about the matrix? So can we say nothing about the matrix? Well, no, we can actually say something about the matrix. So I'm glad nobody wrote nothing. What its associated eigenvector is. If I only know the eigenvalue, does that allow me to know, and by the way, I don't know what the coefficient matrix is, but if all I know is the eigenvalue, how do I find the eigenvector? What would I need to find the eigenvector?
Something else.
Yeah. So what's the process? If you want to find the eigenvector, you've got the eigenvalue. What do you have to do to go from eigenvalue to eigenvector?
You have to use the coefficient matrix.
Ding!
Yeah,
Which we don't know in this case. So if we don't know the the coefficient matrix, then there's no way we could find an eigenvector. Wah, wah. All we know is that the eigenvalue is this 2 plus 3i. So that second one, no, we don't know that one. The third one is what the other eigenvalue is. Surprisingly, that is correct. We are guaranteed to know what the other eigenvalue is because, anybody want to take a stab on that?
Conjugate pairs.
Ding, ding. It's a conjugate pair because if you know one eigenvalue is a complex number, then you know its conjugate also has to be an eigenvalue. So that means if I do my quick share screen here on my document camera, so if you know this one is your eigenvalue number 1, then you're guaranteed to know lambda 2 is 2 minus 3i. That's what makes it a conjugate pair. That the imaginary part is opposite in sign. And do you guys remember from probably pre-calc what makes it a conjugate pair? Conjugate numbers in terms of complex numbers. If you have a plus bi and you multiply it by its conjugate a minus bi, what happens? Oh, I had some of you for pre-calculus. I know you know this.
It gets rid of the eyes, right?
Hey, so what happens is you take two different, but they're complex conjugates, two different complex numbers, multiply them together, and all you get when you multiply them through, when you do this, those middle terms, the a times bi and a times minus bi, those middle terms go away, and you're left with a squared plus b squared. Because the I squared becomes a -1. And so that's the special feature of a conjugate. When you multiply a complex number times its conjugate, you wind up with real numbers. And that's in the backdrop why it is that when we have one complex number and the other one is its conjugate for eigenvalues, they kind of fall apart in our solution. We can always write our solution as being in terms of real values. There's sines and cosines in there, but the real number aspect of them can really take place here. So I'm going to stop the share. And that gets us to, there it is, my polling results over here. So we definitely can say what the other eigenvalue is. The third one says the general solution for the associated system. Well, if we only know one eigenvalue, but we don't know its eigenvector, we can't put together a general solution. We need eigenvalue and eigenvector pair to be able to make a straight line solution. So we can't make a general solution unless we have that. Ooh, the next one is the phase plane's origin is a spiral source. And how do we know it's a spiral source? Many of you answered this, so be confident. You're right. How do we know?
A was greater than 0.
Okay, because the A in the eigenvalue, that's the 2 in the 2 plus 3i, the 2 is greater than 0. So that means if you follow that through, where does it appear in our solution? That's in the exponent of the e to the power. So that's the e to the 2t in this case, which tells us we're dealing with exponential growth. And it's an imaginary, or it's a complex eigenvalue, so we know it's going to be spiraling. It's either spiraling outward or spiraling inward, right? Those are the only two options if you have an a value that's not 0. If a value is equal to 0, it doesn't spiral out and it doesn't spiral in. It just creates these epicycles, right? These usually elliptical orbits. They don't go towards the origin or away from the origin. So good job on that one. We can tell the phase plane's origin is definitely going to be a spiral source. And then last but not least, that the phase plane's origin is a spiral sink. Well, wah, wah. I guess we put that one to bed. It can't be both a spiral source and a spiral sink. Okay, now for the real important part of this quiz. In the 1950s, the combination of this pop and a moon pie. Do you guys know what a moon pie is? Yeah, some of you do. Some of you do. The combination of this pop and a moon pie became known as the working man's lunch in the American South. A moon pie is a dessert. It's like a Twinkie, old-timey Twinkie, but it's with cookies and chocolate, and apparently it's really good. I don't know. So many of you said Coca-Cola. Good guess. It is a cola, but it's not Coca-Cola. It's RC Cola. Yeah. Have you ever had an RC Cola? Yeah. When I was growing up, we always wanted pop, but we could never afford like real Coca-Cola or real Pepsi. And so if we were lucky, RC Cola would go on special and we'd get RC Cola. And I always remember thinking, it's good enough. But, oh well. So yeah, it was an RC Cola thing. Anybody know what RC stands for? An RC Cola? What is it? John, lay it on me.
It's Royal Crown.
Royal Crown. Very good. Royal Crown Cola. Yep. The one that was kind of, I was going to come up with a, that's what I'm looking for, trivia question about Faygo. You guys know that Faygo is a Detroit pop, right? Do you know the other famous Detroit-based pop? Some people don't consider it a pop, but I think it's a pop.
Is it Verner's?
It is Verner's. Nailed it. Good job. Yeah, so Verner's and Faygo are Detroit's contribution to pop history. So there'll be more pop quizzes coming. So make sure you study your pop.
It took me way too long to realize that pop quiz was a. It took me way too long to realize that pop quiz was a play on words.
I've used these before. Come on, I used them in pre-calc. I used them in calculus. Oh, you poor thing. Okay, so the last question, back to the boring math stuff. If a coefficient matrix has 2 positive real eigenvalues, how would we categorize the origin of its associated phase plane? So there's a lot of word salad there to kind of pull apart. It means it's got 2 positive real eigenvalues. Remember the eigenvalues? those appear in the exponential part. They're the upstairs of the exponential. So it's our solution would look like e to the positive something t power, which means you must be talking about spiraling out, right? If they were complex, we'd be talking about spiraling. But notice this goes on and says they're real eigenvalues. So what does that mean? It's not spiraling out. Yeah, it means that along straight lines, two different straight line solutions, because we have two different real values, they're going to be running outward, away. I don't know what direction they're pointing, right? I don't know what direction the straight line solutions are pointing, but I know that its phase plane is got to be looking like a, let me see if I can share my screen. It's going to be looking like this. If we imagine our X and our Y, we know we're going to have, since they're both positive, I don't know what direction these straight line solutions are going, but one of them is going to be going outward, and then you're going to have another one, maybe something like this, and it's always going to be going outward. And that means our origin, we can count on our origin being a source. Right? If they were negative, then we'd be going towards the origin along both of those, and that would be a sink. How do you get a saddle out of this? What would we have to do to make this a saddle point at the origin?
One positive, one negative.
One positive, one negative. Now notice, I didn't say anything about how big these eigenvalues are. All I care is that they're both positive. They're both greater than 0. Right? So if your coefficient matrix has two positive eigenvalues, you know the origin is going to be some sort of a source, right? And if you know they're both real, they're going to be that's going to be a source for two straight line solutions. What if I told you the A value for your complex eigenvalue was negative? What would you predict for the origin? To bring this back to where we were before. That's a real good question, Steve. I really wish I knew the answer. Well, I'm glad that you're still learning and you're still growing and you're still getting a handle on this 3.3 and 3.4 stuff, because surprise, that's what we're going to work on next. So the pop quiz got us thinking about the relationship between the stuff that we learned in 3.1 and 3.2 and kind of expanding on that in 3.3, and then 3.4 takes us into the realm of complex eigenvalues, not just real, but complex eigenvalues as well. And so by the time we're done with 3.1 through 3.4, we've covered a lot of ground. Not all the ground that we're going to cover, because there are a couple of other situations, kind of special cases. It's possible to have two real eigenvalues. It's possible to have two real eigenvalues that are the same number. Because if you think about this, if you get your eigenvalues from that coefficient matrix's determinant, when it's a modified coefficient matrix. So that thing set equal to 0 could give you a quadratic that has a repeated real solution, two that are really the same thing. And we haven't touched that yet. That hasn't come up. That's going to be in 3.5. We're going to get to that one next. And the other situation that we also haven't dealt with is what happens if one of your eigenvalues is 0? What do you do? We haven't talked about that. Those are special cases. We'll get to those later. But right now, anytime you have distinct real eigenvalues or complex eigenvalues, you know what to do, because you've up through 3.4, you've seen the strategies for being able to solve those systems of linear differential equations. So now what we're going to do is I'm going to turn you guys loose in your breakout rooms and give you a chance to work on the assigned on the agenda, the assigned problems. And you'll notice I tried to give different problems for each team. There was a little bit of doubling up on one of the, I think it's the 3.3 problems. But take a look at those and you're going to be tackling those problems, just those two. Then when we get back together, you and your team are going to be sharing what you've got. So just as a heads up, I want you to work together, but I don't want it to be I'm just going to put my screen up and my partner's just going to sit there and go, I don't want you to share screen until you've both worked on something and you think you've got a solution for a particular problem. And then you can share screen. But until then, I don't want you sharing screen. Got it? Okay, it's practice time. We're doing this because I want you to be ready for the game. So let's get in there and do some practice. Okay, so I'm going to open up the rooms. Emma, you're going to have to give me a second. I'll have to add you to your team because you disappeared before I after I'd finished assigning the teams here. Okay, so the rooms are open. It is 6:45. We'll get back together. I'll be in to check on you, but I'm planning on getting back together at 7:15 so we can put these all together here. Let me see. Emma, assigned to, you are in group, not sure. And Steven, where'd Steven go? Uh-oh, Steven disappeared. Emma, I hope everything is okay. Can you give me a thumbs up to let me know everything's okay? Unless you've already disappeared. I'm going to hit pause on the recording since you don't need to watch this later. Okay, so we are back. In many ways, it was like we were always there all along. Our timeline went like this, and then you stopped, and we continued, and then we looped back around to continue right here. So we have like an entire 30+ minutes of history that you, the viewing audience, don't even understand at this point. We're totally different people. You wouldn't understand us. Okay, anyways, enough of that. So let's take a look at...
Aren't we the viewing audience, though?
Maybe, I don't know. As far as I can tell, apparently I have former students watching these videos, so maybe they'll get a kick out of that too. I don't know. And they'll leave me a comment about God knows what. Okay, so we're going to take a look at 3.3. Who had number 1?
That was us.
Okay. So
I'll
number
share my
1, go ahead. Number 1, we have a output for Maple, and the question is, what do we know based on this output? What can we say based on this output? So go ahead, take it away, Palsy.
It says host disabled participant screen share.
Okay, don't take it away, Paul. Okay, now take it away, Paul.
Okay, now okay, so the first part A was pretty straightforward. We just kind of made a matrix. Well, we kind of took the matrix and just added the X's and Y's in.
Okay, so you created the system that's associated with that coefficient matrix.
So, and then part B, we found the eigenvalues and the eigenvectors with Maple.
Yep.
Then we created the straight line solutions, which turned out to be these guys here.
Okay, nicely done. And so notice if you know the eigenvalue and the eigenvector, you can always write the straight line solution. And this is a really important point. The straight line solution is a particular solution. There's no constant sitting in front of it. There's no unnamed, or there's no unknown constant sitting in front of it. It's just e to the lambda t power times the eigenvector. And that's true across the board, regardless of what your lambda and your vector are. So nice work.
So then for part C, we found that the first straight line solution will be more influential because the lambda 1 is greater than lambda 2, and that's from page 35 or 37.
So notice the magnitude of the eigenvector or the eigenvalues is how we determine which one of them is or is not. Now, I don't think, did I ask you to make a DE plot? I didn't ask you to make a DE plot for this. But if you made a DE plot for this, you could look along the straight line, the 2 straight line solutions, and you would see as you look out in the phase plane that if you pick a point anywhere out in the phase plane, that lambda 1 associated straight line solution would be more influential. And so you have to see a couple of examples of this to get a sense of what's going on. So good job. Write the general solution. That was part D.
Yeah. So we used Maple again for that. And then we found both the X and T of Y, X of T and Y of T. And then we kind of combined them into the big Y of T.
Okay. So notice what you have when you have that solution. You have you should have the exact same thing as if you took your 2 straight line solutions, added them together with a constant in front of them. So that should be there. So one of them should be e to the 7t. It's there. Times a constant times the vector. And if you factor out of that, what you've got right there for part D, if you factored out the e to the 7t, you'd have 1 2/3, which is the same thing as 3 and 2.
I guess I could have factored out the e to the 4t also.
Yeah. And as a matter of fact, you didn't need Maple to solve it because you had your straight line solutions already. So you were done at that. So good job. And then E described the origin as a sink source or saddle point.
It said we figured it was a source because they were both greater than 0. And it didn't really turn out this way because it turned out that lambda 1 was greater than lambda 2 actually, but we figured it was just because it was flipped.
Yeah.
Sort of.
As long as both of them are positive real numbers, then you know that origin is going to be a source because everything's trying to get away. It's exponential growth away from the origin as opposed to exponential decay towards. Yeah. So if ever you have a negative eigenvalue, real eigenvalue, you know that straight line solution is going to be headed towards. If it's positive, it's going to be headed away. Here's an interesting thought. What if lambda turned out to be 0? What if one of your eigenvalues is 0? What would that mean for that straight line solution? It can't be headed away. It can't be headed toward. So what's happening on that straight line solution?
Maybe it's just a dot, maybe.
We're going to get there in the next section.
Does it just kind of like stop at the line? Like everything
as a
goes
matter of
straight
fact,
to the line and it doesn't flow either direction?
Well, it's not that it would stop at the line, because remember, you can't become the line. You'd approach
Like it goes to the line.
But if you look at any point on the straight line solution, it's not going to be play the clock forward. It's not going to be moving. Any point on the straight line solution is going to wind up being, I don't want to give away the ending here, but any point on the straight line solution where lambda is equal to 0 is an equilibrium point. Because that point doesn't move in time. It just stays there. As opposed to one of our straight line solutions, like the ones that we were talking about here, where these straight line solutions were headed out away. And so if you pick a point on that straight line solution away from the origin, it's going to go and head that direction over time. So we'll get to it. We'll get to it. Okay, so that's number 1. Good job. Number 2. Who had number 2? I think it was this the one where we had multiple people with number 2. Yeah, we had multiple groups with number 2. So how about we flip a coin and
I can just take it.
Okay, Team Humble. What's this? Is that like that? Right. No, you're pointing at the people. Got it. Go. Okay. Yeah. So take it away, Wyatt.
All right, so this is what we got. The 2, it wanted us to take the eigenvalues and eigenvectors of the 2 systems. So here's the first system, and both systems have the same values as far as part of their matrix coefficients. However, what is it? One was in decimals and one was in fractions, and that we later found is why there was discrepancies between the 2 answers. So to begin with, one with fractions and stuff, since it was given to us in a fraction, that was an exact value. There was no precision past the decimal place. That was the exact value. So that's why it returned it to us with fractions and exact values. And then the second one we tried, we did it with the decimals that we were supposed to. And since it only went to one place past the decimal, it returned it to us with large decimal numbers, and that's because it was accounting for the lack of precision, which was the answer with the numbers that we had in the matrix. And then we got kind of confused why I had this plus 0.I, and we later learned that that is 0 times I. And we also learned that Maple, for some reason, well, we actually learned that reason too, but Maple, whenever you have like a I that's associated with like an imaginary number, it gives it to you as a capital rather than a lowercase. So in reality, this isn't 0.2, 0 times 0 whatever plus 0.I, it's 0.2 plus 0 times I, and 0 times I is 0, so that's what it means.
Nicely put. very good. And you can totally see the same thing happening with your eigenvectors. And so if you look at the eigenvectors, notice that first eigenvector, remember we have to look vertically. That first eigenvector is 1, 1, or excuse me, 0, 0, 1. That's what it is, 0, 1. And then the other one, interestingly, is negative 0.7071 blah, 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 plus 0i, and negative 0.707 plus 0i. So it's the same thing on the top and the bottom. So it's crazy, but that is the exact same eigenvector for the purposes of our work as 1, 1, because whatever's in the top is mirrored by the bottom. And so if you look down on the bottom of the screen there, where they did the eigenvectors with the fractions, Maple gives it to us nice and neat and tidy. It's so frustrating, but that's just the way Maple thinks. You put decimals in things and it's like, decimals, you want decimals? I've got decimals for you. And it gives it to you as a decimal with plus 0i, because of course Maple knows eigenvalues can be complex numbers. So it just goes overboard. Cool. Nicely done. Team, let's see, who's the other team here? Team Brat, did you have anything you wanted to add to that?
Nope, that was pretty good.
That was such a bratty thing to say. And I can say that, you know, in all earnestness. Okay, so that's number 2. How about number 3? Who's going to do this one? I don't know.
Yeah, I don't know.
I don't know. I don't know. Q-dubs.
Yep.
What you got for us?
Okay, let's see. Let's look back at the question here.
Question is, one of your classmates claims that he's found a system of 2 linear first-order differential equations that has 2 distinct real eigenvalues and 2 straight-line solutions that are equally influential on the phase plane. Dun, dun, dun. So write a possible general solution for the system based on the description. And so how can we tell, looking at your solution, that it's 2 different distinct eigenvalues and that they have 2 straight line solutions that are equally influential?
So here's the general solution with the eigenvalues, of course, and then our eigenvalues here are these little things right here, the 2 and the -2.
These little things right here.
Yep.
And so they're different eigenvalues, but they are equally influential because?
Because they're the same amount, they're the same absolute value or magnitude.
Yep, same magnitude means they're equally influential. And we can tell that these are different straight line solutions because?
Because of the negative and positive, maybe?
Yeah. Yep. How else can we tell that they're definitely different? And you did it on purpose. You made them definitely different.
Not coming to mind.
So what's the other part of the straight line solution? The e to the power, that's one part of it.
Oh, and then the vector part.
Yeah.
Right here.
And so they're very different vectors. They're pointing in different directions, so they are distinct straight line solutions. So yay, nice work. So that's part A. Part B was write a possible system of equations that meet the requirements. So how'd you guys do this? What was your strategy? Did you just start throwing things in for eigenvectors and see if you could find a matrix?
Worked backwards, we did B first, then did A.
Got it. Okay, that's smart.
So, just did this thing right here several times until it came out nice.
Cool. And so that has 2 distinct eigenvalues that are equal in magnitude, and also different eigenvectors. So nice work.
So this is it in scalar form right here, and then we just plugged it in to a DE plot to see what it looked like.
Yeah. So what do we got? So how can, just looking at this DE plot, how can you tell that these are 2 distinct and different magnitude, or excuse me, different sign eigenvalues? How can you tell looking at the DE plot?
Just based on where it's pointing towards, one of them's pointing towards the origin, the other one's pointing away.
And so you can tell which one is associated with lambda equals 2. That would be your blue horizontal one because that's going away. And you can tell the other one must be the -2 because it's headed towards the origin. So all this stuff was sitting there waiting for us when we were learning about the phase plane in chapter 2. We didn't have a language to be able to describe what was going on. So eigenvalues, eigenvectors allow us to have that sort of language. And to kind of bring this around full circle, if I said, hey, can you make me a vector field plot? You could go in and do a direction field. But if you made a vector field plot, the fact that those two eigenvalues are equal magnitude tells you that no matter how far out this way or how far out this way you go along those two straight line solutions, as you move out away from the origin, the arrow's lengths are going to be the same along those two straight line solutions because they're equal lambda values. The magnitude is going to be equivalent. Does that make sense? Quentin, you have to speak for the entire class.
Makes sense to me.
I feel like I should be in a Mentos commercial. You know, okay. Okay, so who had number 4?
That was us.
You may proceed.
Here we go. Okay, so it is all this stuff starting here. So
okay.
It was just true or false. It is possible to have two different systems of linear differential equations to have the exact same eigenvalues. And we ended up saying true, and we kind of came up with an example to prove it. So we kind of came up with really simple differential equation systems that are also linear. And so we said dx dt is equal to x and dy dt is equal to 2y, which when you put it in matrix form, you just get this. And when you do the whole determinant setting it equal to 0, you just end up getting 1 minus lambda and 2 minus lambda. So they're really easy to find your two eigenvalues. And then for the other one, we kind of swapped it around. So it's different, but they're also linear again. And they yield the exact same eigenvalues, just different order.
Perfect. Now notice, and I want to comment on not only the fact that, yay, you nailed it, it's possible for two different systems to have the exact same eigenvalues. But look at the strategy that they used. They said, you know what? A system of differential equations could be, linear differential equations could be any number times x plus any other number times y. And then the same thing down here. Oh, it could be really complicated. They said, well, what if we made these really simple? What if we made these equations super simple? And I'm just betting that they probably started by looking at the coefficient matrix, right? The setup as a coefficient matrix, and saying, what if we just had the diagonal had numbers and the others were 0? Because that makes it really easy, right? Because your characteristic polynomial is really easy to find if those C and B and C values are 0, right? Super easy. And it also makes the system decoupled, which is real easy to solve, right? So this becomes a real easy problem, but that's okay. That you don't have to make it super complicated. All you had to do to verify whether this is true or false is come up with one example where two different systems have the exact same eigenvalues. So there was another thing that when I popped in your room, we talked real briefly about another approach that you could have taken with this problem. Do you remember what it is that we were talking about?
I don't remember when you said a different approach to think about it.
Well, I didn't say a different approach. I just said one way you can think about the eigenvalues is that they're coming from the characteristic polynomial. Sorry, all these words in my head. The characteristic polynomial, right? And so basically when we say, is it possible for a system and two systems to have the same eigenvalues, but be different systems? It's equivalent to saying, is it possible for two quadratic equations to have the same zeros, but be different quadratic equations, right?
Right.
And so of course the answer to that is, well, yeah, you could have a parabola that's like this, or a parabola that's like this, or a parabola that's super skinny and tall, or upside down. And all of those could possibly have the exact same zeros as a quadratic, but they'd be technically different quadratic equations. So that's another way you could have approached this problem, is to say, what are the eigenvalues really? They're just the zeros of a quadratic. Does that make sense?
Yeah.
And since you speak for everybody, thank you. I'm glad. Ding. Okay. Lovely. Excellent work on that one. Okay, so we're moving on. We're in section 3.4. And as is what happens when you multiply an imaginary lump of feces times I, shit gets real. Okay, so who had number 1 on 3.4? That's a joke grenade that'll go off later. Some of you will get that. Imaginary feces and multiply by it. Anyways, who had number 1 in 3.4? Did Alana get that joke? Did Alana get that joke? She wasn't listening. She's over here. She could have benefited from that. What happens when you take an imaginary piece of feces and you multiply it by I? Shit gets real. Get it? Shit gets real. She said it's cute, which is about all I can expect from her. Anyways, 3.4, number 1. What you got for us?
Well, we just took the eigenvalues of each of the matrices and then just kind of looked at it.
Okay.
And said what it was.
So 2 complex eigenvalues. But then you have a question mark for the second one. What do you mean by that?
That was because of this thing, but why it explained it, like this 0.I thing.
So really, the eigenvalues for that one are 2 real eigenvalues. One of them is 4.5, blah, blah, blah. What if you were like, God, I really like to have exact eigenvalues? What could you
took
do?
these into fractions instead of...
Give it a shot. While I've got you here, go ahead. So how do we turn 1.3 into a real fraction here?
Okay, let's see. 1.3. So... I'm
telling you, yeah, somewhere there's an elementary school teacher going, come on, Quentin, I know you can do this.
Yeah, I know.
Look at that. And boom. Ooh, look at those. Ooh. But you can see how they're coming from solutions to a quadratic equation. You got some number plus a radical, and it's all one fraction, right? And so these are just simplified, but you can see kind of where things are coming from. Now, you would never guess those are the exact values for the decimals you just saw a second ago. There may be times when you want exact values, but there are probably equally times when you want a decimal equivalent because you got to make sense of it, right? So if I said, which one of those 2 is a larger number? You'd be like, I think maybe the one that's plus. Right? And you can quickly tell if it's in decimal form. You can quickly tell which one is the larger magnitude just by looking at them. So nice work. So you stumbled into the same mix when we're talking about how to read the output for Maple on that one. So nice work. Okay, number 2. Who does number 2 work for?
Me.
Okay.
Okay, hold on.
So this one you had to expand using Euler's formula. Boom, boom, boom.
Yeah, Chris kept saying Euler.
Oh my God, does he do it on purpose?
No, he said that's what I think when I see it. I'm like, okay, that's fine.
Yeah, but I mean, I don't think Harris when I see his name. So anyways. Harris.
So we had to expand this using Euler's formula. And starting off, we had this here. Using the formula, we then took it to the EA times EIB. We decided that 3, of course, is the A, and pi is the I. Or pi is the B, and there's the I right there. Moving on to the third step in the formula, you see our work here. E to the A times cosine of B plus I sine of B. Giving us, then we did the math here, cosine of pi was just 1. And the sine was 0, so we have a 0, and then our final answer appears here.
Nice. So here's an interesting thought. You can stick an imaginary number in the exponent, and it turns out to be a real number, a real value. This is one of those moments where you really should stop and marvel at this, at how could that possibly make sense? Because an exponent, as we've learned all these many times in our math explorations, just means repeated multiplication, right? 3 to the second power means 3 times 3. 5 to the third power means 5 times 5 times 5. But what the hell does 3 or e to the 3 plus I pi power mean? That can't possibly make any sense. And what you see right here is the e to the 3 part, that makes sense to us. But the e to the I times pi power is just -1. How? How do you take a real number, raise it to an imaginary power, and have it be something meaningful? Welcome, my friends, to complex numbers. There's a whole realm out there of mathematics that we're going to make use of. And this is really the first chance that most of you probably will have had to make use of imaginary numbers. And I don't want to spoil the ending, but if you're going on in any kind of applied mathematics or further in mathematics in general, you will be dealing with imaginary numbers in the exponent, and it means something marvelous and wonderful, and it's not something that we can cover in this class because it takes too damn long. But it's totally worth watching a video that I posted about it. If you haven't had a chance to watch it already, it's really cool. How about the other one?
Well, the other one was not as easy because we had a t in there. But using your example that you so graciously provided for us in the notes, thank you, we again split up a and b, but this time the t is attached to both as we did that. And then following Euler's formula, we performed the same operation, giving us our answer here.
Yeah, and notice this time the I sticks around, right? Because that sign just doesn't disappear and become 0. So we actually have 2 terms. The first term is a real, e to the -3t times cosine 2t. That's a real value function. The other one, because it's always multiplied by I, it's always going to be imaginary. So we have a real part plus an imaginary part. Nicely done. Yay. Very mechanical, but important for us to know how to do that stuff. Okay, how about number 3? Number 3, we're going the opposite direction. How do we work backwards from expanded to condense it down into an exponential? Who had number 3?
Okay, I will show you. So, like you said, 3 was just kind of going backwards with the Euler's method. And so we found that b was the square root of 2 and a was 0. So it was really pretty simple. All it was b to the square root of 2 times 5 with 3a.
Yep.
And for b, we found a was 2t and b was 5t. So it was just b to the 2t plus 5ti.
Nicely done. And of course, you could factor out the t if you wanted to. And that would be e to the 2 plus 5i in parentheses times t. And then that would look kind of like an eigenvalue times t upstairs there. But yeah, you don't have to do it. But yeah, that's absolutely correct. Nicely done. So being fluent enough to be able to work forwards and backwards with Euler's formula, that's just something you got to get used to. And you're going to do enough problems, you're going to be working through these, where hopefully it's just going to become part of your routine. But again, nothing becomes part of your vocabulary unless you use it on a regular basis, which is why every day I wake up and I say disestablishmentarianism, because someday I'm going to actually use that word in polite conversation other than saying it like I just did there. I've never really come up with a reason to know that word, but okay, how about number 4? Twice as good as number 2. I might even go so far as to say the square of number 2. Who's up?
That is correct, and it proved to be true in the end.
Ooh,
so
go on.
Team Humble being twice as good as number 2 and 4 times as good as number 1.
You, of course, would never say that, but I take you at your word.
Well, that's just what I've heard other people say.
That's right. I've heard.
Wyatt mostly, but
everybody's saying it.
Yeah. So anyway, we got given this thing. It was I plus square root of 5 as that was the eigenvalue. We got two parts. Question A was, what is its other eigenvalue? And so that would be negative I plus the square root of 5.
Ooh, you didn't get tripped up by my trickery.
No, we're too humble to be tricked. And
Notice,
then,
though, the important thing is it's the imaginary part that's negative for the complex conjugate. So
yeah,
good catch.
because alpha and beta was 1, and yeah, it's a whole set. Yeah. Anyway, part B was a particular solution curve for this same system is of differential equations is plotted on the phase plane. What can we say about the solution curve qualitatively? And the answer we came up with was that it will spiral away from the origin. And we said it's going to spiral away because A is positive. Again, A being the square root of 5.
So
and then
it goes away from the origin because A is positive. The spiral bit comes from
the imaginary part.
The fact that it has an imaginary part.
Yeah.
Nice, nice. So one of the things that you can think about as you're trying to wrap your head around this whole imaginary eigenvalue thing is that all the real number eigenvalues that you've ever seen and solved for, those technically are complex numbers, right? If your eigenvalue turned out to be lambda equals 2, it's technically lambda equals 2 plus 0i. So you can still say it's going to move away from the origin because of the 2, and because the beta is 0, it's not going to spiral at all. It doesn't spiral, it just moves away from the origin. Does that make sense? So the bigger that beta is, the more you expect it to see that kind of spiraling take place. So, How about number 5, a true and false question? So easy, so simple.
We
Come on, Brad.
Yeah, we got something, but it's not. It's a hunch.
You know, when I ask a true false question, it's going to be a real bruiser. So,
So basically, we kind of use page 47 from 3.4, I believe. You were kind of confused, but I think our hunch would be that when we get like an imaginary number in our eigenvector, that we could get a cosine or sine as a particular solution. Not super confident, and I couldn't explain why. But it's just a pattern we saw, I suppose.
So you're looking at the idea of, is it possible to get cosines and sines in a solution? And the answer to that is absolutely. All you need is to have that eigenvalue have an imaginary component, right? As long as that imaginary part isn't 0, you're going to get the spiraling, right? Or the periodic motion. It's either going to be spiraling outward, or it's going to be spiraling inward, or it's going to be just kind of moving in orbits. So if you have an imaginary part of your eigenvalue, you definitely are going to see motion around on the phase plane. But if we look closer at the solution that I gave you, what do you notice about those two periodic functions?
Well, to me, the 2t kind of threw me off.
So what do you know? What's different about those two? The one's a sine and one's a cosine, yes. But what do you notice about the difference between those two? If you were in trig class, how would you talk about them as being fundamentally different?
Well, the cosine would be 2 times as the sine.
So what about it is 2 times? You're on the right track, but what are you talking about here?
Fantastic question.
So the thing inside of a trig function, so cosine of that thing in there is called the argument of the function, right?
Okay.
And so if it's cosine of 2t, how is that different than cosine of just t? How does that thing inside there affect, think about the graph of the cosine function. Cosine of 2t versus cosine of t. You can graph it on Maple right now or watching. So if you were in Maple and you decided you wanted to plot cosine of t and plot, you're going to have to do it with the in math. Yep. So if you just said plot parentheses cosine 2t.
I don't know if any with
There you go.
plots, but
It never hurts. It never hurts to have it on there. Ooh, plot B. And so if you say plot cosine 2t, and then we do cosine or plot cosine t. Those of you playing the at-home game, you may have a hunch about this, but what we're about to do is kind of verify this. What do you notice? This is the same scale, by the way, negative 2 pi to 2 pi. What do you notice about these two graphs? How would you describe their difference?
is the period that's 2 times as fast?
You nailed it. So don't think of it as the period is 2 times as fast. Think of it as the period for the cosine of 2t is shorter. It's technically the language is it's a higher frequency wave. It's happening more frequently. So back to the problem, the true-false problem. It says, is it possible to produce a solution that has cosines and sines? And the answer, as we've seen many times, is sure, yeah, you can produce a solution to a system with cosines and sines. You just have to have an imaginary eigenvalue or an imaginary part to your eigenvalue. But the catch is you cannot produce from a system, you cannot produce something that has cosines and sines with different periods, because that period inside the cosine and the sine is the second part of your eigenvalue, right? Because remember, the lambda is alpha plus beta times I. The alpha tells me whether it's expanding, it's getting bigger, or it's getting smaller, or it's 0 and it's staying at a constant, or just an orbit. But the beta is what determines the period. The beta is what appears inside the cosine or the sine function. And so looking at that solution that's on the page, it says the solution x of t would be equal to cosine of 2t, and y of t is equal to sine of t. They have different periods. Try as you might with a linear system, you will never get a linear system to produce with multiple frequencies, right, on the sines and the cosines. It's just not possible. It's a really subtle thing, and you did exactly what I hope you'd do. You focused on the fact that they're trig functions, but I want you to also see, hey, look at that fancy guy with snow skis. I wanted you to focus also on the fact that they're different periods, and the period for those periodic functions is coming from the eigenvalue itself. So how are we feeling about that? Thank you for sharing. How are we feeling about that? Did that make sense? Kind of how we constructed that argument? The eigenvalues tell us two things, because every number is a complex number. They tell us whether something's moving towards or away from the origin, positive or negative alpha. And then if that beta is anything other than 0, it's telling us it's cycling at a particular period. And every trig function in our solution, every trig argument in our solution has to be based on that beta value, right? Sneaky, but useful. Can I be excused? My brain is full. How you feeling? Good? You ready to get in there and give it hell? The next problem set? You gonna give problem set number 9, the old 1-2, knock it on its butt?
I think it's going to give me the 1-2.
Yeah, you got to get in there. Just take it. Then you get back in there. Sorry, Emma, you're not showing up. So this has just turned into like major testosterone fest in here. So, oh, there she is. Okay, suddenly I feel calmer and more soothed. See, what you don't know, guys, is that Emma is a black belt in no fewer than 3 martial arts. And she has like upper arms that will squeeze you into a paste that 4 out of 5 dentists wouldn't recommend for anything. She's a bruiser. She really is. She's amazing. So don't lip off to her. She'll really get you. So she's like, no. So, well, thank you. If you have any other questions, I'll stick around. But we got through, surprise, surprise, all of the classwork, and that was awesome. The only other thing that I would want to suggest is if you have a little bit of time, you want to stick around and work in your groups or ask questions about problem set 9, you can do that. Also, planning ahead for exam 3, a week from today, we're going to be right at the end of class. I'm going to say, go forth and finish your exam. And I will give you the exam, and you'll have from Monday through to Wednesday, I think at 5:30 is what I'm saying, because I give it a little bit of a buffer there. So it's going to be a quick turnaround on the Chapter 3 exam from Monday to Wednesday, or quicker than usual. So I just wanted to give you the heads up on that. If you scroll down on the agenda, you'll notice that there's a link to the exam 3 review, which contains the exam 3 classwork and the review and the suggested exercises are all there. So if you're running out of things to keep you busy over next weekend, you've got plenty of stuff to work on. Otherwise, I'll be around if you need me. Even if you don't, I'll still be around.
Is the test going to be teamwork or just individual?
It's going to be completely individual. I decided I'm not going to go with a teamwork on this one just because of the turnaround is too small. We are going to have another investigation, but it's going to be after we're done with the exam. So that'll be the next thing right after the exam that we work on. So cool. Cool. Well, I'm going to hit stop on the recording, and I'll stick around if you have any questions to ask. Otherwise, I'll just sit quietly, pouting that you all left me. Take care, guys.